Hello, everyone. So my name is Mohib Zara. I'm a senior developer advocate for the serverless team. And in this demo, we're going to talk through an Amazon SageMaker example notebook and see Amazon SageMaker Autopilot in action. If you've ever worked with machine learning before, you know that data cleaning, pre-processing, and trying to find the right combination of hyperparameters for the algorithm you choose is very time-consuming and can be intimidating for beginners. SageMaker Autopilot is a new SageMaker capability that can take your data set and explore numerous machine learning approaches to help you find the best predictive model. And let's look at how easy it can be. So for this example, I'm using a modified version of the sample Amazon SageMaker notebook called Targeting Direct Marketing with Amazon SageMaker XGBoost, which is available in the Introduction to Applying Machine Learning section of Amazon SageMaker's example notebooks. This notebook has been modified to make it easier for me to walk it through with you, but you can explore the full notebook yourself in Amazon SageMaker as you wish. The objective is to train a machine learning model that can predict whether or not a potential customer is likely to respond to a specific direct marketing engagement. We're going to start with a typical setup. You'd start importing some Python libraries, specifying an S3 location, region, and IAM role to work with, nothing too special. Next, we'll download and extract the dataset, which is published by the University of California, Irvine in their machine learning repository. Let's take a quick look at the data and see what we have to work with. A dataset consists of about 41,000 examples containing 20 different pieces of customer demographic information like age, job, marital status, etc. And these properties are called features in the context of machine learning. We also have this Y value on the far right, which indicates whether or not the marketing campaign this person was part of resulted in new business from them. The value in the data set is called a label, and it's what we want to train a machine learning model to predict. Easy so far, right? Well, this is usually where the easy part ends. We have a good amount of data, but it might not be suitable in its current form to use right away. And I say might not because we literally don't know yet, and we have to do some work to find out. And part of this process is called data analysis and preparation. It's where we need to go through and check on a lot of things. For this example, it says, we don't know if this person in the second row has ever defaulted on credit. And are there more people like this? Should our model take these unknown values into consideration? Or do we only care about cases where we know the answer is yes or no? And what about the rows where the value for that feature is missing entirely? Do we exclude those rows completely, or do we try to substitute sensible values? And what about other properties that might be the case? So we need to look at which of our features are numeric and which are considered categorical. The algorithm we're using for this demo doesn't understand plain string values like hi.school, married, telephone, and so on. We need to go through the data set, identify, and figure out how to convert these values into numeric values where needed. And what about data types? The age and PDAY values are numbers, but they are represented as numbers in the CSV file that we downloaded. Or does the CSV have them as quoted text that would treat it as strings? We need to go through and check on that as well. And once we're done with all that, we need to look closely at the distribution of values in the data set and try to determine what kind of impact each of the features might have on the actual result that we're trying to predict. And are there any features that don't have a strong correlation with the outcome? Even if a feature does have a strong correlation with the outcome, will that information be available to us in the future when we're actually trying to make predictions using our model? And are there any redundant features? And so on. This is a lot of work that can take a lot of code to perform. And depending on your data set, here's just a little bit of code from the sample notebook showing how you'd create all of the charts to analyze. And once we've analyzed enough and understand the transformations that need to be made, we'd use the rest of this to convert our categorical values, drop irrelevant values, etc. Fortunately, this particular example data set has already been cleaned pretty well, but we could easily find ourselves having to write tons more code or less orderly data sets. Now let's see what the code for data analysis and preparation steps look like when we're using SageMaker Autopilot. That's right, we don't have to do any code for the data preparation step. We're going to leave it all up to SageMaker Autopilot. Let's prepare our training data. All right. So we're going to give SageMaker 90% of our data set to use for training purposes, and we'll keep 10% of it behind to use as a test set of data to evaluate the final model on our own when everything is done. Behind the scenes, SageMaker Autopilot will automatically split off a portion of the training data that we give it to as validation data for checking the quality of all the different approaches it's going to be exploring. Let's start the training job. Here we're telling SageMaker where to find our training data on S3, and we want to be able to predict the value of Y, which is whether or not the direct marketing engagement with the customer will be successful. Next, we'll tell it where to put the output. And finally, we'll tell it when to decide to stop exploring and give us a result. In this case, SageMaker will keep looking until it has found 10 possible models. And this can take a long time to run, so once the job starts, we'll keep checking on its status by using the snippet of code and the AutoML job name value, which identifies the job. This will keep running until it finishes, fails, or gets stopped early. And while we wait, I want to tell you about another amazing feature of Amazon SageMaker Autopilot. I've already told you that SageMaker is going to handle data analysis and preparation, and that it's going to explore different approaches in order to recommend some model candidates for us. But what exactly does exploring different approaches mean? Machine learning models are trained using machine learning algorithms, but there is a seemingly infinite number of ways you could tune each of these algorithms using values called hyperparameters. That would cause them to produce better or worse results. The XGBoost algorithm that SageMaker Autopilot uses in this demo, for example, has dozens of different hyperparameters that can either significantly improve your model or make it almost completely useless if not tuned properly. How does hyperparameter tuning work? Well, normally we need to decide on which hyperparameters we want to tweak, pick a few different ranges to try, and then create a SageMaker hyperparameter tuning job like this. But in this demo, we're not going to have to do anything like that because hyperparameter optimization already comes built in with SageMaker Autopilot. It already did all of this for us behind the scenes. We can go into the SageMaker console and browse through the different training jobs that were initiated by the hyperparameter tuner, and we can see how long each tuning job took to run, where the transformed input data came from, and what metrics it's gathering throughout the process, and which hyperparameter settings it checked during this job. This AutoML job took about 30 minutes to complete, and now that it's finished, we can take a look at all the model candidates that were trained for us. This code will show us all of the candidate model names, which metrics SageMaker used to determine how effective it was, and the value of that metric. We have 10 possible models to choose from, and the best one had a validation accuracy of about 0.9134 when it was used to make predictions on the validation data set that SageMaker Autopilot split for us. Now we can take the best candidate, look up its metadata from the AutoML training job that discovered it, and use its inference containers setting to save it as a separate model. Now we can deploy our model by creating a SageMaker endpoint, and once deployed, our application will be able to use it to make predictions. And to do that, we first defined an endpoint configuration that specifies how many instances of which type we'll need, as well as a model variant name to use for that endpoint. Variants are helpful in situations where you might be working to improve your model, and you want to increase the number of requests that go to a new endpoint gradually, while leaving the existing endpoint still serving a majority of inference requests. So think of it like A/B testing. Since this can take a few minutes, we'll use the same snippet of code from earlier to keep checking and let us know when it's done, but it usually takes around 10 minutes, but this is a recorded demo. So if the business case for this machine learning model requires it to handle periods of higher than normal load, we can choose to configure the endpoint further by going to the SageMaker console and setting both an auto-scaling policy and limits on instance counts. Now, we can use the endpoint to make predictions with the test data that we held back and see how well the model works. We'll run through all the examples in the test data, check them against inference endpoint, and then take note of the predictions and actual outcomes or labels for evaluation later. And once that's done, we can calculate a few metrics and display what's called a confusion matrix to see how good of a model SageMaker Autopilot will build for us. And a confusion matrix for a binary classification problem like this one is a table that shows us all of the predicted and actual outcomes for our test data set at a glance. Those outcomes are called true positives or true negatives, false positives, and false negatives. But as the name confusion matrix suggests, this can be a bit confusing, so it's helpful to think about it this way. A positive is something our model predicted would happen, and a negative is something our model predicted wouldn't happen. If the model predicts something is going to happen and it does, we call that outcome a true positive. When it predicts something that isn't going to happen and it doesn't, that's called a true negative. Both of these are desirable outcomes. A false positive, on the other hand, means the model predicted something would happen, but it didn't. A false negative means the problem predicted something wouldn't happen, but it actually did. In both cases, the model's prediction was wrong. Basically, we want to see as many true positives and true negatives as we can. So let's see the numbers for the model SageMaker Autopilot trained for us. First, the good outcomes. We have 3,525 true negatives and 280 true positives. So the model correctly predicted that 3,525 people would not respond to the marketing campaign and that 280 people would. For the bad outcomes, 187 of the people that it predicted would not respond to the campaign actually did, and 127 of the people it predicted would respond to the campaign actually did not. And we can interpret these results further by looking at these additional metrics: accuracy, precision, recall, and F1 score. There are about a dozen different metrics that you can compute from a confusion matrix to help evaluate models, but these are 4 of the more commonly used ones for binary classification problems like this. A few of them may appear similar at first look, but there are subtle differences that can make it easy to get them mixed up. So instead, let's compare these results to the results of the model that we would have ended up with if we followed the instructions in the sample notebook I showed you at the beginning of this demo. We can see here the model trained by SageMaker Autopilot achieved higher accuracy and precision than the model from the sample notebook. The value for recall was similar, and the F1 score was considerably higher. We had far less code in our notebook that uses SageMaker Autopilot, so getting a much better model with so much less work is a great result. And this is good, but can the results be better, or does this mean we don't need data scientists anymore? And it doesn't. This isn't magic. An experienced data scientist can put in the work to train a better model, so if that's what your use case requires, then that's what you're going to need to do. SageMaker Autopilot can still make their jobs easier by giving them a great head start towards a high-quality model. They can then review data transformations and recommendations made by SageMaker Autopilot, which are all saved in Amazon S3 by the AutoML training and tuning jobs. And then you can iterate from there. This level of accuracy you saw here is good enough for your needs, though, then you can build yourself a really good model fairly quickly without the help of a data scientist at all. And finally, I'll make sure to clean up after myself and delete all of the resources that were created by this demo. And I hope you enjoyed this demo and are excited to take some time to give SageMaker Autopilot a try on your own. And thank you for coming.